All right, chillins and chickadees, it's been a while since we've been able to have science. We left off in chapter 1 on lesson 1 and 2, talking about speed and calculating average speed and things like that. Now we're going to be looking at the last section, chapter 1, lesson 3 in our books on acceleration, which also connects to speed. It's a very short section. It won't take very long at all to get through. And then we're going to get into chapter 2, lesson 1, where we're introduced to the idea of force, what force is, and how we calculate our net force. So please make sure you're taking your notes. Please make sure you're writing it down in your book or on notebook paper. That way, when you go to do your assignment or any future tests, like maybe a standardized test next week in science, you'll remember some of these things. So let's get started with chapter 1, lesson 3. So acceleration. Acceleration is probably a word that you've heard before, and especially if you're into vehicles and engines, you'll know that a brand new sports car can go from 0 to 60 in like 2.2 seconds or something like that. Well, that's acceleration. Or it could be a moving vehicle from one point to the next, wanting to know how long it took to accelerate going a specific distance or up to a specific speed. We need to know three different things when we're doing acceleration. We need to know our final speed, our initial speed, and the time that it took. Right? So what that means is when we do final speed, we're at a specific time that we're looking at it. And then how fast did it get there? So when I look at a sports car, as I first example I said was going from 0 to 60. So my final speed I know is going to be fixed on a 60. Or maybe you see a vehicle flying down the road in front of your house and you want to try to calculate what the acceleration was as it sped up to go past your house. You would need to know the final speed as it's in front of your house and then its initial speed, right? So when we find speed, we're taking our distance divided by time. In our vehicles, we talk about miles per hour, right? When we talk about other areas in the world outside of those three countries, then we talk about kilometers per hour. But our initial speed is looking at a time when we first spot it. It could be at a stop sign, then it's 0. It could be testing on a test track to see how long it takes to go from 0 to 60. So I know it's going to be 0. Or maybe it was, 3 houses down on our road and it seemed to be going pretty slow, and then all of a sudden it sped up to go past our house. So we want to know what that initial speed was, and then we'll compare it to our final speed. And then the final thing that we need to know is how long it took, right? The amount of time. Could be seconds, could be minutes, could be hours. So when we do acceleration, it's all about doing a math problem. So when I look at the idea of a speed limit, right? So I know that I have a speed limit of 55, and that's what I want to get to. But we're sitting behind a vehicle that is slowing down. We might get a little irritated as a driver, maybe you as a rider, maybe you're late for a practice or you're trying to get to a game or something and the people in front of you seem to just be continuously slowing down. And then we realized, oh, there's a stoplight that's red, so they're slowing down as they approach the intersection. So then we should be okay with it. As we look down, we're going 35 miles per hour as we are slowing down also. So at 35 miles per hour, that's going to be what we refer to as our initial speed. Because I know I want to get to 55 when it turns green. When that light turns green and I start to accelerate, I want to know how long it takes. Well, we're going to say it took 10 seconds to go from 35 to 55, which is the speed limit. So when I do acceleration, once again, just like with speed, it is a math problem. When I know my final speed and my initial speed, then I just plug those in into this formula. Final speed minus the initial speed divided by the time that it took to go. So when I set up my math problem, I know that my final speed was 55 because I got up to the speed limit. I started out at 35 because I had to slow down at the red light. And when I looked at my clock, it took about 10 seconds. So then I just simply do my math. Order of operations tells me to do 55 minus 35 first, and that's going to give me 20 on top. I keep my 10 at the bottom. So now I have 20 miles per hour per 10 seconds. But I need to divide because I can't keep it that way. So I would just divide and I would see that 10 goes into 22 times. Now, when you get into classes like physics or advanced science, then you'll talk about how you can do a different calculation with miles per hour per second. But we're not going to worry about that in sixth grade. When you get older, you can discuss that one. But you would basically end up finding out that you went 2 miles per hour per second to go from 35 to 55. Right? So just the idea of understanding what acceleration is. I'm taking final speed. I'm going to take my initial speed from it, and then I will divide by my time. Right? I just need to know how long did it take on average, because this is an average problem, going from my slower time to my faster time. That was it. I told you it would be really quick. All right, so getting into chapter 2, lesson 3, kind of switching gears a little bit. We're going to get into the nature of force and what is force, right? So we got to remember that when we talked about some of these things, so in chapter 1, lesson 2, we talked about velocity. And we said velocity was a speed and a direction. So keep that in mind that we had a direction indicating which way it was going to go, right? So we gave the example of the police chase going 87 miles per hour in a northwest direction. So when I know that then on velocity, then when it comes to force, I should be able to connect to the idea that I need two pieces of information. First, the very basic definition of force is simply that it's a push or a pull. When we talk about gravity, it's a push or a pull, right? So the sun's gravity is a pull. The center of the earth is a pull. When we jump out of an airplane, the center of gravity, being the earth, pulls us down through the air, down to the ground. Hopefully you pull out your cord and your parachute works. So the idea of force is simply to push or pull. All forces create motion, and all motion is created by a force. When we talk about force, then, we're going to describe it with a strength, so that's going to be its measurement, and a direction in which that push or that pull, that force is going. So we talked about the SI, right? We need to learn that SIs, or the International System of Units, we know that the SI for distance all over the world, other than, if we were talking about our measurements in the US, right? We're using the metric system, right? So we have a meter. When we talk about force, well, that's not something that we normally test. You usually get into a specific type of trade or job, or you're a scientist when we talk about measuring force. But the SI adopted unit is what we call as newtons. So if I talk about this apple and I'm going to drop it, then I need to understand that there's a push or pull on the apple, right? So in order to lift the apple, there's going to be a push of it going up. When I let go of the apple, there's going to be a pull going down because gravity is going to pull on it. But all motion is caused by forces. I've said that a few times. When I talk about the SI unit, then a force is going to be measured in what we call a Newton, and its label is just a capital N, right? Newtons. So if I talk about 1 Newton, that is going to be the strength part of labeling a force. I said we had to have two things, just like we had speed and direction for velocity. Well, for force, we need a strength and a direction. So I need to know which way it's going. So if I let the apple fall, then I'm going to show that my arrow, my Newton, my pull, my force is going down. Arrows are always going to tell me the direction that the force is going. So if I have a specific force then I talk about the next topic, which is a net force. So a net force is combining all forces together on a specific object and then determining what direction the object might go. So the book talks about a non-zero force. Now, some of us, we get a little frustrated because that word, it just seems weird. It doesn't make any sense, but it means truly exactly what it says. A non-zero force just simply means any number more than zero. So don't get freaked out about seeing something that says non-zero. It's not confusing. It means exactly what it's saying. Anything greater than 0. 0.01 is a non-zero force. Up to a billion, zillion, trillion, whatever you want to say. As long as it's more than 0, then that's what we're talking about. So when we talk about our overall net forces, then we're talking about combining different things that are applying a push or a pull on an object and seeing what the overall force is going to be and direction it goes in. All right, so let's look at what we're talking about. In our book, we have examples of dogs pushing on a box of dog food or dog treats. We can see that the arrows are indicating to us that the dogs are pushing. It's indicating to us the amount of force, right, labeled in newtons, that the dogs are using. We have 16 newtons for the spotted dog, and we have 10 newtons for the little black dog. They're both pushing in the same direction because the arrows are pushing in the same direction. Notice the size of their arrows. The bigger the arrow, the more force. The smaller the arrow, the smaller the amount of force. So when I talk about net force, then I need to combine the forces and know if that combining means adding or subtracting, depending on which way the forces are going. In this case, they're both going in the same direction. If they're both going in the same direction, then I'm going to add them together. Basic math. 16 plus 10 gives me 26 newtons. The other aspect to it, we have to also indicate the direction it's going in. And they're both pushing in the same direction, so I'm going to have a bigger arrow because I combined my forces, and we're going to point to the right because that's the direction that they are leading you. Both are considered non-zero numbers because 10 and 16 are both greater than 0. Hopefully that was pretty easy to understand. Look at your next picture in your book. Now we've got the same two dogs pushing with maybe different amounts here and there, but they're going in opposite directions. Right? So if a net force is combining the forces given on an object, then it should make sense if we step back and think logically what's going to happen to that box, since the force is greater on top because it's a taller dog. It's actually going to topple over and dump out all over the little dog. But when they're going in opposite directions, the amount of force that causes it to topple over, I'm not going to be able to combine those in addition. I have to subtract them. The dog is pushing to the right, the black dog's pushing to the left. I have to subtract their forces. 20 minus 10 gives me a nice even 10 newtons. Then I have to indicate with an arrow, and I have to indicate which direction the force will end up going. Not both forces because they're going in opposite directions. So it's the force that's left over. Since it's the big dog that has more force, it has to go to the right. Notice we have a smaller arrow. Once again, smaller arrows, smaller forces, larger forces, it means we have to draw a larger arrow. All right, so when I look at how those are combined, right, then I should be able to see that the 26 has a bigger arrow than the 10. But now let's look at what happens when I'm going in opposite directions with the same amount of force. We have twin dogs. They're both pushing towards the center of the box. It's mine, it's mine, it's mine, it's mine. Where's the box going to go? Well, once again, net force is combining the forces applied to it. They're going in opposite directions, right? So in opposite directions, I'm going to subtract. And when I have 10 minus 10, I end up with 0 newtons. So how would I draw the arrow? Well, if I have 0 newtons, then that means the object will not change. It's not going to move. They're both just going to keep pushing on that box until they get tired and fall down and take a nap. Right? So I don't have an arrow anytime there is 0 newtons. If there's anything more than 0, even a 0.01, I have to have an arrow indicating which way it's going. So what about this example? Right, so I have two dogs. The big dog, once again, is pushing 20. The little dog, he has 0 newtons, right? So the non-zero would be the 20 from the big dog actually touching the box. The little black dog, maybe he's a little goofy in the head or he just doesn't know what's going on. He's not actually pushing against the box, right? So there's 0 force coming from him. Therefore, when I combine those together, I can add or subtract because the little dog's not affecting the box at all. I know it's going to go 20 newtons and it's going to go to the right because that's the direction that the big dog is going. Hopefully all this was really easy to understand, right? Hopefully it wasn't difficult at all. So just to recap the idea of forces, forces is any push or pull, and forces are what causes all motion within our world, within our solar system, within the universe, galaxy, and everything. When I talk about forces, then I need to be able to describe its strength. Once again, we have a label for that, and the direction that it goes with an arrow. So if I know that my SI, my International System of Units, is the Newton, then I would label the force. When I drop that apple, we could say that it was 1 Newton, and the arrow goes down. Net force is then the combination of forces on a specific object, right? So we need to know what the amount of force is and the direction that the object may be moving overall. We could have a situation, once again, where it's not going to move at all, right? So we have to be able to do the math. All right, so when we look at the assignment, you can either do the digital copy that I have on Canvas for you, or you can do the paper copy that I'm going to give your teachers today. I would like them tomorrow, which is April the 29th by 2:20 before you go home, so I can grade them and add some more points, hopefully really good points to your science grade. Thank you much.